Hello, and welcome to section 11.3, where we will discuss the integral test for convergence. The integral test uses improper integrals to approximate series, and thus allows us to relate the convergence of the improper integral to the convergence of the series. Before we state the test, recall the definition of the improper integral. The integral from 1 to infinity of f of x dx equals the limit as t goes to infinity of the integral from 1 to t of f of x dx. Then the integral test says, suppose that f is a continuous, positive, decreasing function on the interval 1 to infinity, and that f of n equals a of n where n is an integer. Then, if the integral from 1 to infinity of f of x dx converges, then the sum n equals 1 to infinity of an also converges. And if the integral from 1 to infinity of f of x dx diverges, then the sum n equals 1 to infinity of an also diverges. Note that the function f must be positive and decreasing for this to work. Let us build some intuition as to why this test works. First, let's investigate the first statement. If the integral from 1 to infinity of f of x dx converges, then the sum n equals 1 to infinity of an converges. Consider the following figure, which shows the graph of the decreasing function f with integer points f of n equal to an marked. At each of the integer points n, we form a rectangle with height f of n and with base length 1. It follows that the area of each box is precisely f of n, and the sum of the area of the boxes is precisely given by the series the sum n equals 1 to infinity of f of n, which equals the sum n equals 1 to infinity of a sub n. We have essentially performed a right endpoint approximation of the area underneath the curve, and hence the sum of the areas of the boxes underestimates the area underneath the curve. The area underneath the curve is given by the improper integral, the integral from 1 to infinity of f of x dx. So if this area is finite, or if this integral converges, then so is the area enclosed by the boxes. More precisely, we have shown that the sum n equals 1 to infinity of f of n, which equals the sum n equals 1 to infinity of an, equals a1 plus the sum n equals 2 to the infinity of an, is less than or equal to a1 plus the integral from 1 to infinity of f of x dx. So if the improper integral converges, then so does the corresponding series. For the second statement, we perform a similar procedure. If the integral from 1 to infinity of f of x diverges, then the sum n equals 1 to infinity of an diverges. Instead, we now overestimate the area underneath the curve and perform a left endpoint approximation as in the figure. Thus, the sum of the areas of the boxes, which is represented by our series, overestimates the area underneath the curve, which is represented by the improper integral. Hence, if the improper integral diverges, then so does the series. Let's perform some more concrete examples to illustrate the above procedure. The following figure represents the series, the sum n equals 1 to infinity of 1 over n squared. The series underestimates the area underneath the curve. Thus we have the sum n equals 1 to infinity of 1 over n squared is less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared dx, which equals 1 plus 1, which equals 2. Therefore, the series, the sum n equals 1 to infinity of 1 over n squared, is convergent. For another example, consider the harmonic series, the sum n equals 1 to infinity of 1 over n. This figure shows how the harmonic series overestimates the area underneath the curve 1 over x. Therefore, the integral from 1 to infinity of 1 over x dx is less than or equal to the sum n equals 1 to infinity of 1 over n. And we know that the left integral diverges, hence the harmonic series diverges also. Let's do an example. Determine whether the series, the sum n equals 1 to infinity of the natural log of n divided by n converges or diverges. First, note by L'Hopital's rule, the limit as n goes to infinity of the natural log of n divided by n equals the limit as n goes to infinity of 1 over n, which equals 0. So we cannot use the test for divergence. We use the integral test instead. let f of x equal the natural log of x divided by x. We need to verify the assumptions in the integral test. F is certainly continuous on 1 to infinity and positive, and f of n equals a of n. But is f decreasing? To show that f is decreasing, we compute the derivative and verify that it's negative. F prime of x equals x times 1 over x minus the natural log of x divided by x squared, which equals 1 minus the natural log of x divided by x squared. Note that f prime of x is less than 0 if and only if 1 minus the natural log of x is less than 0, which is if and only if 1 is less than the natural log of x, which happens if and only if e is less than x. Thus f of x is decreasing when x is greater than e. Since e is approximately 2.718, we need to ignore the first few terms of our original series and apply the integral test to what remains. The sum n equals 3 to infinity of the natural log of n divided by n. We now compute the improper integral. The integral from e to infinity of the natural log of x divided by x dx equals the limit as t goes to infinity of the integral from 1 to t of the natural log of x divided by x dx, which equals the limit as t goes to infinity of the natural log of x squared divided by x evaluated from e to t, which equals the limit as t goes to infinity of the natural log of t squared divided by t minus 1/2, which equals infinity. By the integral test, since the integral from e to infinity of the natural log of x divided by x dx diverges, then so does the series, the sum n equals 3 to infinity of the natural log of n divided by n. Since the sum n equals 3 to infinity of the natural log of n divided by n is less than or equal to the sum n equals 1 to infinity of the natural log of n divided by n, we conclude that our original series diverges. We conclude this section by exploiting the idea behind the integral test to actually estimate the sum of a convergent series. The idea that we exploit is the fact that the integral test is really approximating infinite areas by series. As before, let f be a positive, decreasing function, f of n equal an, and suppose that the sum k equals 1 to infinity of ak is convergent. Define Rn to equal the sum k equals 1 to infinity of ak minus the sum k equals 1 to n of ak. Rn is simply the difference between the sum of the series and the nth partial sum. It is called the remainder, or sometimes referred to as the error in approximating the series. Notice that Rn equals an plus 1 plus an plus 2 plus an plus 3, etc., which equals f of n plus 1 plus f of n plus 2 plus f of n plus 3, etc. And thus, via a right endpoint approximation, we obtain that Rn equaled fn plus 1 plus fn plus 2 plus fn plus 3, etc. is less than or equal to the integral from n to infinity of f of x dx. Similarly, by instead doing a right endpoint approximation, we obtain that Rn is greater than or equal to the integral from n plus 1 to infinity of f of x dx. Therefore, we conclude that the integral from n plus 1 to infinity of f of x dx is less than or equal to Rn, which is less than or equal to the integral from n to infinity of f of x dx, where Rn is the remainder. This allows us to measure how close the nth partial sum, the sum k equals 1 to n of ak, is to the actual sum of the series. Example 2. Use the sum of the first 10 terms to approximate the sum n equals 1 to infinity 1 over n squared. How good is this estimate? The sum of the first 10 terms is the sum n equals 1 to 10 of 1 divided by n squared, which equals 1 plus 1 over 2 squared plus 1 over 3 squared, all the way up to 1 divided by 10 squared, which is approximately 1.549768. To verify how good of an estimate this is, we need to compute the remainder R10. We have that R10 is less than or equal to the integral from 10 to infinity of 1 over x squared dx, which equals the limit as t goes to infinity of negative 1 over t plus 1/10, which equals 1/10. Therefore, the error of the approximation 1.549768 is at most 1/10. Note that we can use the inequality, the integral from n plus 1 to infinity of f of x dx is less than or equal to Rn, which is less than or equal to the integral from n to infinity of f of x dx, to improve our estimate even further. We have that R10 equals the sum n equals 1 to infinity of 1 over n squared minus the sum n equals 1 to 10 of 1 over n squared, which is approximately the sum n equals 1 to infinity of 1 over n squared minus 1.549768. Thus our inequality becomes 1/11 equals the integral from 11 to infinity of 1 over x squared dx, which is less than or equal to the sum n equals 1 to infinity of 1 over n squared minus 1.549768, which is less than or equal to the integral from 10 to infinity of 1 over x squared dx, which equals 1/10, which we can rewrite by adding 1.549768 throughout the inequalities. We get that 1.640677 is less than or equal to n equals 1 to infinity of 1 over n squared, which is less than or equal to 1.649768. Therefore, the sum is approximately the average of the left and right quantities. The sum n equals 1 to infinity of 1 over n squared is approximately 1.640677 plus 1.649768 divided by 2, which is approximately 1.6402.